The second one is sorting light metal tons faster with LIBS. I'm really interested in the non-ferrous market. We have a couple of clients that I got to work with in the last year. And I started with Reynolds, so Reynolds aluminum, and worked with screens and different kinds of systems on separating alloys. So really interesting to hear what they have to say. Steve Buckley is Vice President and General Manager of Applied Systems, Ocean Applied. Steve?
Great, thank you, and it's super nice to be here. We're actually, my first slide doesn't say much about our company, so I'll say a little bit now. We're actually from Orlando, and so Orlando-based company, global footprint. The team that works on what I'm going to talk about today is actually based in Rochester, but we have offices in Germany, China, and elsewhere. So super glad to be here. So I think for those of you who've been in the industry for a long time, you know some of the challenges of sorting metal fractions. In particular, we're going to talk today about the light metal problem, and that's where our LIBS technology really shines. As you probably know, just because of wanting fuel efficiency and things like that, light metals are increasingly being used in autos, in obviously aircraft and things like that. And so the primary aluminum is hugely carbon intensive. I mean, the numbers are stunning, but 2 or 3% of the world's energy is used to manufacture primary aluminum. And so there's been a big focus in the last 5 years or so on reducing the carbon intensity of the aluminum that's being produced worldwide. And so and also minimizing bauxite mining, which is obviously also polluting. So to do that, obviously, we want to increase the recycled fraction in aluminum that's being used for new aluminum. And so what we're looking at is how can we get better fractions at the scrap processors? How do we separate wrought from cast? How do we separate different classes of aluminum, 5,000, 6,000, 7,000 series? And how do we look at specific alloy compositions and extract those from a general pile of aluminum scrap? And so you may be familiar with typical sensor-based sorters for metals, right? And most of the traditional ones use X-rays. And they have over-the-belt, XRF, XRT, and these are great for non-ferrous, for ferrous sortation, heavy metals, and you can use eddy current, obviously, to separate the ferrous, and then you can also get fractions using X-ray. But the problem is that X-rays don't work well on light elements. What do I mean by light elements? I mean like magnesium, aluminum, silicon, obviously carbon's a light element as well. And so in the last probably 10 years, there's been increasing interest in LIBS. And what is LIBS? LIBS is Laser-Induced Breakdown Spectroscopy. That's a mouthful. But the breakdown that we're talking about is actually the spark in the picture right there. So you can see, so that's how it got named. It's a laser basically firing on a material, making a spark. And then in that spark, as I'll show you on the next slide, you'll actually see how we get emission from that, and that's how we analyze the metal, right? So the process is super simple. You have something you're shooting at with a laser. That's this, let's see if I can get the laser to work here, this laser. So you're shooting on something, you're making lots of small particles. Just like when you're welding, if you've watched welding, you see the fume come off. Those are also tiny particles, right? Same kind of thing, produced by a plasma. So the laser hits the material, makes lots of small particles, and then the laser's pulsed, the laser makes a plasma. So the little particles end up in the plasma, right? That's the spark, that's the breakdown in LIBS. And then you have all this emission that comes out, that's the visible that you see from the spark. And in that, there's different lines that make a spectrum corresponding to the different elements in the metal that you shot at. And so using this, we can then analyze pieces of scrap at a really high rate. And so this is just on the right here, you can see sort of and this will play as I talk, but you can see sort of a sortation happening in real time. These are scrap pieces, and you see in this little area here, you'll see little flashes, not always well captured by the video, but you'll see flashes as these pieces get hit by the laser. And so if you were to design a sensor-based sorter, what would you want? Well, you'd really want to have really high throughput. You can see this is a very high throughput process. You'd want a flexibility to handle pieces of various sizes and shapes, because anybody who's seen stuff coming out of a car shredder, you know that even the mid-cut, it's all bent up. Sometimes we get window frame material, we get all kinds of different material. You'd want few or no moving parts so that you could maximize your uptime, talking about in the previous talk about shafts versus the finger sortation. And you'd want to be able to blast through dirt and coatings. A lot of the scrap that we sort is not perfect. None of it's perfect, really. And then you'd want something that's pretty easy to maintain with a good sortation ability to separate between the fractions that you want, maybe wrought versus cast, 5,000 versus 6,000. And you'd want something that you could get ROI from in a matter of months. So we put our heads together, and we're an optical sorting company, really optics and photonics company. We said, well, we think we can solve this problem, and so we designed something that we call the speed sorter, which is this box right here. And maybe to go back, I should just say the speed sorter is behind and under. I'll show you another video in a moment. It's behind and under this chute. So we're shooting our laser from underneath this chute into this region where all these pieces are coming, right? And so you'll see that better in the next couple slides. But we designed the speed sorter, which is the sensor that does the LIBS-based sortation. So the speed sorter, the laser comes out here. It's got all, on the back, it's got all the kind of connection that you would need. And each of the speed sorters can do about a ton per hour of metal sortation. It's really good at reliably detecting oxidized, dirty aluminum, coated aluminum, because it's a pretty high-powered laser. The laser inside here is also used for cutting metal, so it's kind of a demon-type laser. Don't want to get in front of it. And it's a very modular design, so we can stack several of these things all in a process, as you'll see, and it doesn't have to do anything like an autofocus, so there's no moving parts. So I'll go a little forward. So again, the basic concept is you've got the pieces falling down. They fall down in front of the laser. The laser fires at the piece, and then during this tiny distance between, say, 3 and 4 here, the laser spectra is collected. This computer inside says, okay, what kind of aluminum or magnesium do I have? Okay, I know now. And then it fires a diverter, and it either, well, or not. So either the piece falls down into fraction number 5, or the diverter fires and it falls into fraction number 6. So it's made for, ideally, it's made for a binary sort, although we have several customers now implementing this with a multi-sort on a more of a conveyor in a different orientation than this, not with falling pieces, but that way they can do a multi-sort, so they can sort 5,000, 6,000, and 7,000 series all at once or something like that. So I'll show you here one of the integrations that we've done with our partner at Austin AI. We've worked with several different integrators, so this is just one. This one is neat because it does allow for single or multiple lanes, and you can sort of expand your sorting capacity. So some people start with just 1 or 2 lanes full with just 1 or 2 of the sensor sorters, and then they'll add lanes to that. And so the hardware from Austin is accommodative of different amounts of, different basically sizes for your system. And let's see, so the next one, this should be a video. This will kind of give you an overview of the whole process. And what you'll see is that the pieces coming down the conveyor, they get the vibratory feeder, they go onto the chute, multi-lanes. So each of these lanes has a different speed sorter working for it. And you'll see in each of the drawers here, we can accommodate 3 different speed sorter systems. So 6 total in the full system. And as they go in front of the laser, they get fired, either they drop or they get ejected. So very few moving parts, really no moving parts. Vibratory feeder, if you count that. And we found that this is really an effective system. We have a number of systems in Europe right now, one sorting just 6063 from general pile of scrap. We also have systems working with primary aluminum producers as well as secondary aluminum producers, just doing, say, 5,000, 6,000. But the neat thing about this is you can really dial in the chemistry that you want. So the problem that you're really trying to solve is maybe you want to sell your scrap to a secondary smelter, right? And they want to then produce a high-value aluminum grade. You might want to pull only the 6063, or you might want to pull things that look like 6063. There's a whole bunch of, to get the chemistry approximately right. And so in the software, you can basically, this is a little complicated, but we have it, this each speed sorter then connects to a mothership with PLCs. The software can basically allow you to set thresholds so you can discriminate between different alloys of aluminum, right? And so each of the systems can be monitored individually. You can set thresholds. You can basically adjust the chemistry on the fly. So you can do one sort one day, one sort the next day, or even per hour if you have different loads coming in. And you can monitor multiple systems. It'll kind of tell you the health of the system and things like that as well. So it's set up for integration into a factory system or just a standalone with a PLC, a readout right on site. So really the goal is to create value here for sorting, for scrap sorters. And the difference between mixed aluminum scrap and high-value alloys can be a lot, as you probably know. It can be $500 a ton, $1,000 a ton, even if you hit the market at the right time. And that allows this system to have a really high ROI. You know, and the payback period is usually 6 months, 8 months, depending on utility, how much you're using it, and what you're sorting. But with the ability to set your own recipes, you can do different chemistries by day, and you can get the right chemistry out pretty much every time. Kind of the different value for different parts of the market. You know, if you're a scrap processors, you know, you're going to want to be able to sort, say, 5,000 from 6,000. You want to look at a specific chemistry to deliver it to the secondary producer. If you're a secondary producer, you know, you want to maybe just produce a wrought alloy, and so you want to get the right fraction into your smelter. And even for primary producers, you know, the big guys like Alcoa or Hydro, they all have low carbon product now, and so as input for the low carbon product, you need to have a recycled fraction that you understand the chemistry of. So in each of those sort of value streams, there's something for everybody in using the speed sorter. So I think that's all I have. So if you have any questions, be happy to take them.
At the end.
Yeah, I will do questions at the end. There we go. All right, then, well, I'll give it to you. Thank you.
So just a couple points here. Excuse me. 6,000 series is a wrought aluminum. It's low copper generally. And think of the extrusions at your house that you have in your windows, the window framing. That's the kind of aluminum. 5,000 series is common cast, but it's also can tops, which is a 5,000 series out. 8,000 series is like foil, which doesn't tear easily, but you make it really thin and malleable. And they're all different chemistries. And what's the second part of this is what's its application to single stream? Well, we have black plastic, right? And the same kinds of technologies that you're hearing here, X-ray and spectrometer type technologies. Black plastic is used because it has a good display property in the shelf, and it shows your product really well. But it's made of almost every single kind of plastic. These are the kinds of technologies that are going to get us out of that because they really get down to the chemistry. And they add value when they get down to the chemistry. The closer the chemistry is to pure polyethylene, pure PET, polypropylene, et cetera, the more you're going to get as operators. And it's coming. There are MRFs that have X-ray and optical and near-infrared on the same optical sorter for plastics. And so those days are coming close, and thank you very much. It was a very good explanation. And so we're going to go to the third one, how hypervision technology can help solve difficult problems such as differentiating between plastics and EPR auditing. So this ought to be fun too, and a little closer to home for some of these folks. So thank you very much. We have Eric Cameron, CEO